Good morning, everyone. Welcome to our second day of press conferences and third day of the EGU2018 General Assembly. Our first press conference today is on forests under pressure, and unfortunately one of the speakers had to cancel, but we have two brilliant speakers here with us today, so I hope you enjoy it. And I'll just like to remind everyone that our online press portal is media.egu.eu, and we'll be uploading throughout today a few documents there relating to today's press conferences. There are already some available. And for those of you watching us remotely, you can ask questions using the chat window below the video. And so I'll now introduce our speakers and then hand over to them, and they'll present. And after the two presentations, we will open the floor for questions from journalists here in the room. So our two speakers are Douglas Morton, who is an Earth System Scientist at the NASA Goddard Space Flight Center in the US. And then we have Claudia Hartel, who is a research associate at the Johannes Gutenberg University in Mainz, in Germany. And I'll hand over to them now. Thank you.
Thank you very much, Barbara. Well, it's a great opportunity to share some of our ongoing work. I'd like to share some studies that we've got from Alaska to the Amazon that are using an airborne remote sensing technology called LiDAR. And that gives us a three-dimensional picture of forests as well as their changes over time. And that's really opened a new avenue for science, as we've long had field plots and satellite remote sensing. And now with this airborne set of tools, we're able to make detailed three-dimensional maps across large portions of forested regions that have been inaccessible to us, partly because of the remote regions, partly because we're talking about some forests where the canopy dynamics are happening 50 or 60 meters above the ground, and that's where it's very difficult to make those measurements from the ground. So from an ecological perspective, I'm talking about sort of a fundamental aspect of how forests function. We've wanted to know for a long time how forests are changing, and the major forest change happens when a canopy tree falls, creates a new gap, and then allows new species to move in, establish, and then take over that site. That's partly the process that keeps forests as dynamic as they are, creating different habitats, creating different areas for different species, different composition. But our understanding of that process has been woefully limited. And so we've been trying to answer some of these fundamental questions about how common these forest gaps are and how do they change in space and time. And so the studies I'll share with you today sort of approach those two questions in a way that I think allows us to use this new airborne technology to really change the way we approach the question, especially when we think about the way we represent forests in an ecosystem model. So from our work, gaps are quite rare. They're small and they're dark. And those three things together are sort of a big challenge to the group of people thinking about how forests operate and how we represent forests in our models of the Earth system. Forests are also incredibly dynamic, but they're not dynamic in the way that always creates a gap. You can think about that canopy surface as a bit of a battlefield, although we'll hear more about that later. One that's difficult to characterize and quantify, and I'll share some of our insights from our LiDAR perspective here. But these changes are happening in a way that allow us to better capture the impacts of large disturbances like droughts or fires or hurricanes, as well as understand the fundamental aspects that differentiate forests from the boreal zone down into the tropics. So the technology I'm talking about today is an airborne LiDAR, which is a laser ranger that allows us to fire between 300,000 and 500,000 laser pulses per second. Those laser pulses then are returned off of leaves and branches that help us create a true three-dimensional depiction of the forest canopy from the top of the canopy down to the understory vegetation and the ground. And as we take these measurements, as we fly along at about 120 knots, about 300 meters off the surface, we create this three-dimensional map. If we return back to those same locations year after year, we can start to identify the subtle but important changes that happen as you lose a large branch from the canopy or a large tree fall. So this set of images covers an area of about 16 hectares, and you can see the small red outlines for areas that have changed in this zone of tropical forest over just a one-year time frame. So these are the fundamental processes, these new gaps and these new changes that drive our changes in carbon cycle and that drive our changes in spore species composition, because these are new resource environments. In a recent study that came out just this last week in New Phytologist, we looked at an area of the central Amazon that was exposed to drought conditions during the 2015-2016 El Nino. And by looking at this area of two 1,000 hectare transects of LiDAR data, one inside a national forest and one outside, we're able to understand the fact that during the drought conditions, the amount of canopy turnover from branch fall and tree losses increased by 65%. But somewhat unexpectedly, that was occurring across all of our different size classes, whereas some of our drought experiments, some of our field manipulation studies have suggested that really the tallest trees should be the most sensitive to drought. We didn't see that in our study. So this is where our airborne LiDAR data and the natural experiments that are occurring under drought conditions give us a much better understanding of what drought conditions mean for tropical forests. Closer to home, this is a forest that's in Maryland, close to where I live in Washington, D.C., a research site that's managed by the Smithsonian. This happens to be a young and recovering forest, only about 100 years old, and it has about some of the slowest turnover we've seen from a canopy perspective of any of the sites where we've mapped between the Amazon and Alaska from our airborne system at NASA. And this is a site where those slow but subtle changes are probably yet to happen as this forest reaches maturity. If we come up to Alaska and we look at these small crowns for white spruce trees, you can see that the individual changes we're seeing now aren't so much the individual branches, but our whole trees being lost in this forest over this 5-year time interval. And the rates of changes in these boreal forests actually seem to be accelerating based in part on the warming climate and also based on the increased impacts of insect outbreaks and disease. Just one final example. It's been a busy year for our team. Our airborne crew has been flying a lot because there have been some substantial fire and hurricane damages across the U.S. So this is a site where we had collected data in southern Florida across mangrove forests and where a hurricane, Irma, came ashore. The field photos there give you a depiction of what forests 5 months after a hurricane still look like in terms of the limited amount of recovery in these mangrove ecosystems. And where I was showing you individual gaps, the kinds of things that are created from an individual branch or a tree fall, if we look at the changes across this area of mangroves in the Shark River region of the Everglades, 40% of the canopy areas were damaged in the ways we would consider to be new gaps or changes. In fact, the only areas that you see on that right-hand image where there were less damages in the post-hurricane environment were the forests that were submerged along the margin of the water. As the sea level surge came in from the hurricane, it actually protected those mangrove trees that were closest to the water. So there's more I could say, but I'm going to leave it there. Put up 2 quick links that show our data. We share those data online because there's a great opportunity to use these data for a wide range of science applications, and our group certainly doesn't have all the ideas.
Yeah, hello to everybody. My name is Claudia Hartl. I'm a geographer, or I'm rather a dendrochronologist. I'm doing my postdoc at the Institute of Geography at the Johannes Gutenberg University in Mainz. So, and today I will present our study about warfare dendrochronology. So, because we found that trees are witnesses of Tirpitz attacks in northern Norway. So what we found in our study is that the effects of one military engagement during the Second World War are still evident in the forests of northern Norway more than 70 years later. So how we came up with this study, so we have a quite huge tree-ring width network in North Scandinavia. And in the summer of 2016, we went to the Kafjord and did some dendro sampling. And when we went back to the lab and we measured the tree rings, when we realized there is a very, very narrow ring in the year of 1945, and that's quite uncommon for this region because we know how the growth pattern is there because, as I said, we have a quite huge tree ring width network there. So here is an example of such a tree. You can see here, that's the ring of 1944. And I don't know if you can see it because it's really narrow. Here is the tree ring of 1945. Here is again 1946. So here again a line so that you can see it maybe a little bit better. So yeah, we were of course when wondering why is that. So what was the cause of this exceptional stress response of these Pinus sylvestris trees in the Kafjord in 1945? Well, we asked a colleague from Tromsø, so in Norway, it's also a dendrochronologist, and asked him, if he knows what happened to these trees there in 1945. And then he said, during the Second World War, Tirpitz was there. So the Tirpitz was a German battleship, and it's the biggest battleship which was ever built in Europe. And it's not just that the Tirpitz was there, but the Tirpitz was a major threat to the Allies. And of course, the Allies wanted to destroy this ship. So because of this, they did several air attacks. So it were 5 air attacks in 1944. And what the Germans did to hide the Tirpitz, they used artificial smoke. So that's an acid. And this acid had, of course, caused damage on the trees. Well, we went there then again because in the summer of 2017 and did some further sampling to see how far this damage was. And you can see here the car fjord here. Here was the anchor point of the Tirpitz when we did some sampling here. So that's site 1, and we sampled some other sites with increasing distance to the Tirpitz. So on the whole, we have 5 sites. And when we went back again to the lab and measured the tree ring widths, and we found for the site 1 that 60% of the trees didn't produce a ring in 1945 because they were that much damaged. So when with increasing distance to the anchor point of a Tirpitz, we have less missing rings. So at site 2, we still have 50% of trees didn't produce a ring in this year. And then with increasing distance, again, still 10% of trees didn't produce a ring. But if we then go further, the next sites, so the green and the gray line, they are 6 and 7 kilometers away from the Tirpitz anchor point, and they do not show a strong growth decline in 1945. Well, these are just chronologies and just some bars of missing rings, but we also looked at the growth behavior, so the growth change. And here you can see again site number 1, so we have 100% growth decline in 1945. And it takes the trees 12 years to recover from this strong damage just because of this artificial smoke. So on the second side, we still have very strong growth decline. Then on the third side, so that's around about 4 kilometers away from the Tirpitz anchor point, we still have more than 50% growth decline, and trees need around about 8 years to recover from this impact. And then on the other sides, so that's site 4, it's 6 kilometers away, some of the trees were still affected by this damage, but some just didn't care. And on the fifth side, so it's it's behind a hill, more or less, so the trees did not respond to this artificial smoke, so they were not affected by that. Well, and here, that's again the mean growth of the first sites, just the average growth, so it's basal area increment, and you can see very clearly that we have this very strong growth decline after 1944, and the trees takes them quite long to recover again. But what I want to show you here is that one single tree, or actually these are 2 trees I want to show you, but this tree in orange here, this tree had 5 missing rings, so it didn't grow for 5 years, but afterwards it still again started growing, so that it really recovered, and that I would say that's a really resilient tree. But more impressive is this tree, because it was a tree with quite high growth rates, but when in 1945 it showed missing rings, but also in the 8 following years it didn't grow, but afterwards it recovered again, but it took 30 years to recover from this impact. But it's still there, this tree, it's still alive, and it shows, now today it still shows high growth rates, and I think that's a quite impressive tree. Well, to some concluding remarks, we found in our study that the artificial smoke used to hide the Tirpitz caused the pine forest surrounding the car fjord a very strong and unusual growth decline, especially in the year in 1945, but also in the following years. We found that this damage extended up to 4 kilometers away from the tear pits. And in the most extreme case, tree growth was really interrupted for 9 years. And we think that these results could help us to evaluate the potential environmental impacts of the Second World War, also on other forests in the European theater. Well, thank you.
Thank you very much for these two fascinating presentations. We'll now open the floor for questions. Are there any questions?
Hi, of course. Jonathan Amos, BBC. I mean, the obvious question is what was in that? What was in that fog, smoke, whatever it was, that caused so much damage to the trees?
Yeah, that's chlorosulfic acid, and this reacts with water in the in the vapor, and this then gets to what's the word in English? Salzsäure and Schwefelsäure, sulfic acid and salt acid, and that causes strong damages. And we think that the damage was on the needles then, so that the trees lost all their needles, and because of this they couldn't do photosynthesis in the following years, and because of this they can't produce biomass. Because of this they have missing rings.
Marlo Hood with Agence France Presse. Just following up on that last question, were you able to detect any of the chemical composition by looking at the trees themselves, or is that something that you found out just through historical research?
No, that's just, we found this out through the historical documents. And of course, maybe they used also some other chemicals to produce this fog. And we want to measure the chemical elements in the wood, or we already did it, but the results are not finished yet. So this will be further results, and hopefully we will have some results and can maybe see the elements in the wood then of the trees.
So it's possible there could still be some trace, you just don't have that data back yet.
Yes.
What you're saying.
Yeah,
Okay.
yeah. Maybe we can see it.
And I'm just curious, before somebody sort of filled in the blank for you and suggested the connection with the tippets, what were some of the things that you speculated about? Because I imagine you were quite curious as to why.
Yeah. Usually, so it's quite. No, it's not quite common, but we can see this at some sites that we have lots of missing rings, but usually such missing rings are then connected to insect outbreaks, for example, because insects also feed the leaves or whatever. And but here, so we know it very well with the pine grove in North Scandinavia, and we don't know of any insects there. So we don't have any missing rings in this region. So because of this, we knew, okay, this couldn't have been an insect, this must have been something else. Something must have happened to these forests, a strong impact.
And just one last one, if I may. Do you know whether this fog actually killed any trees? Is there any way for you to know that?
Yeah, we think so, that these also killed some trees, because we can see this in the age of the trees, because we have some trees which are popping up in the 50s and 60s. So we think that there were maybe some gaps then, because some old trees died because of this artificial smoke. And then there were some gaps, and the young trees could grow then. So we can see this in the age structure of the trees.
What kind of gaps
Yeah. This would be quite interesting to apply this to a site.
Douglas, you suggested that the hurricane surge came in and protected the trees at water's edge. Did I hear that right? Are you saying that the water came up so high that the trees were then not knocked over by the wind?
That's exactly right.
They were literally buffered by the water?
They were.
Okay.
And so those tend to be shorter trees that grow at the water margin.
Okay.
They encounter a fair amount of daily variability in terms of tides, and even stronger surges outside of hurricane conditions. But the sea surge that came in with Hurricane Irma along the west coast of Florida was so high that it mostly or completely submerged a number of those trees.
Wow. And so are there any implications for that, from that for recovery behind that area? Is that some sort of a natural barrier that then enables more recovery or any other spatial patterns that you're kind of seeing that might be associated with recovery?
So one of the fascinating things about each of the studies that I discussed today is that our understanding of the forest dynamics is just one piece of a larger set of science questions. In the case of southern Florida, where sea level rise and water pumping has created a condition where the land is sinking and the sea is rising. And so the question is, how does a big storm event like Hurricane Irma kind of reset that whole landscape in terms of making it more or less vulnerable to future storms and future damages? Some of the areas that I showed that weren't recovering are interesting examples where from that sea surge as well as from the damage to hurricanes, seawater that got in has started to concentrate. As it evaporates, it kills more trees, also changes the soil chemistry, and may predispose that area to becoming not a mangrove forest, but now an open patch of saline water. So our team is working to better understand the changes directly to the forests, the changes that we actually can observe with the same LiDAR data in the surface elevation. So the game for us with LiDAR data, anytime we want to study trees, we have to find the ground first. And then we estimate the height of the tree returns above that ground surface. So we've been able to take a look at some of the changing sedimentation and then the erosion caused by storms alongside some of the changes in the structure of forests above them. And that whole kind of landscape is now reset in a way that is something we think about it with other large-scale disturbances, localized in the case of the study here, but also large scale from fires, other storm damages, insect outbreaks, etc. This just happens to be one with such dramatic winds and water that you change not just the canopy, but also the ground elevation.
Thanks.
Hello, Milan Ilic. I write for Delo, a daily paper from Slovenia. Dr. Morton and Dr. Hartl, when I see you together, I have to ask you something about more recent example of warfare dendrochronology, where U.S. government was also involved in the Vietnam War. There were huge amounts of defoliants put on the Vietnam forests in order to eliminate the leaves. To have a greater visibility of the ground from the air, and do you know, is that scientifically now the consequences? Are they scientifically researched in the meantime, or did you have an idea or motivation to do that as well?
So I'm happy to weigh in first, but I'd love to hear what you have to say as well. One of the amazing things about doing work at NASA is that we have an ability to go back pretty far in time. You don't get to do that very often other ways, but the earliest data records from our satellite data are in the early 1970s. And so some of the activity you're discussing actually happened before our environmental monitoring satellites were collecting data. And so there's not an easy way from the satellite perspective to study some of those impacts directly. The curious thing, and I'll put this to my colleague, is that there are some tropical forest trees that do create rings, and there are some tropical forest trees that don't regularly create those rings. And it's created quite a bit of controversy in the community, and there are new tools available to us to make have better certainty in terms of the isotopic composition of the wood that would help us trace back to specific dates like you're describing. I'm not involved in any of that work in Southeast Asia, though.
Yeah, I'm also not involved in such work, but I think that there might be already some ecological studies which analyze something like this. But yeah, so from a dendrochronological perspective, so we need tree rings, and in the tropics, as he already said, not a lot of trees have annual rings because they grow the whole year, so that you don't see a clear tree ring border. But for example, with isotopes, stable isotopes or something like this, you can maybe see something. And also maybe with chemical analyzers, that would be interesting to analyze. Thank you.
Quick one, Douglas. Is ISAT-2 going to be any use to you, or is the footprint just too big?
So ISAT-2 will be a new satellite launched this year that will help us better understand global patterns, similar laser technology, but with a slightly different set of instrument characteristics. A bigger footprint, as you mentioned, about a 10-meter footprint, but also a different wavelength of light. So it'll be a green laser And for most of our work using lasers to study vegetation, we prefer a near-infrared laser because the vegetation is much more reflective in the near-infrared wavelengths. And although it's brightest in the green, which is why we see green leaves, it still reflects just a small proportion of that energy. And so we're eager to use the data whenever possible. And I do expect that we'll be able to make sense of the data over some of the boreal forest areas that have more open canopy. But I'm a little concerned about our ability to use it in tropical forest case, for example, because, as I mentioned earlier, if we don't have information about the ground surface, it's difficult to estimate what the structure of the returns is above that ground surface. And it's very difficult to get green light to penetrate all the way through a dense, multi-layered tropical forest canopy all the way to the ground.
Are there any additional questions?
A question for Douglas, a two-part question, actually. Does the technology, the laser technology that you showed us, have the potential, or perhaps it's doing it already, to fill in any gaps in our understanding of climate change impacts? And I'm wondering whether it might have an application, for example, in terms of monitoring REDD+, the reduced emissions from deforestation and forest degradation, the UN program basically to try and reverse deforestation, whether it might have an application in monitoring those programs, which are quite controversial still.
It's a great question. Yes, actually, much of my work in the Amazon does focus specifically on impacts of forest degradation, which has been part of the more challenging part of implementing the REDD+ agreements. Agreements to reduce the carbon emissions from deforestation are relatively straightforward, and monitoring deforestation has been one of the successes, I think, of the satellite remote sensing community in terms of its application in a direct monitoring context for treaty work. We do have work that allows us to identify the areas that have been logged. You have to work with me here in your imagination, but one of the great things about the LiDAR data is we are creating a three-dimensional cloud of points, and we can slice that like a cake in any layer we look for. The mechanical logging that's done in places like the Amazon creates tunnels through the understory as you move through with a tractor. So as you look for that lowest layer of the forest, you can find the patterns where the tractor has moved in to take out the logs based on the fact that there are tunnels through the understory. And as we slice the LiDAR data to look for those tunnels, we can see the places that have changed in the understory. So we actually do use this exact technology to identify areas where there has been both legal and illegal logging, as well as the fact that one of the challenging parts for REDD+ is to understand not just the initial damages to the forest, but also how those forests recover over time, because the emissions you would take as a part of your credits or penalties depend in part on how fast these forests can recover. So we have another set of studies that have specifically looked at forests in the Amazon that have burned and how fast that carbon recovers. And it takes quite a long time, more like 30 to 50 years to recover most of the carbon stocks that were initially there after just a single wildfire. And the LiDAR technology allows us to make these same kinds of estimates from a carbon and a structure standpoint over areas that will now give us the kind of inputs we need for REDD+.
Just to make sure I understand correctly, then the LiDAR technology is able to detect sort of tunneling underneath canopies that remain intact, which would then, those logging activities would remain opaque or invisible to satellite images, for example. So you're seeing something that we haven't been able to see before. I just want to make that explicit.
That's correct. And so I showed some examples where we can identify from year to year the canopy trees that are missing. In this case, I can take the information from the LiDAR data about the canopy trees that are missing, and I can connect that with a tunnel that goes from the understory perspective to that location. Essentially, it looks like a dendritic grid of a river network as the skidders are pulling the trees out. So I can actually identify the canopy tree itself, as well as the fact that it was connected to that understory forest damage from the actual mechanical logging activity. And so it allows us to take an example where if our imagery only were capturing the top of canopy, we might see a concentrated area with more trees that are missing, but now we can directly connect that using the LiDAR data from the lowest canopy profile to say that those trees are gone because they were removed by mechanical skidding.
Thank you. Are there any additional questions? If not, we'll finish here. You are welcome to approach our speakers. There are 4 interview rooms available if you want to interview them. Our next press conference is on the 2017 exceptional wildfire season, so it's a nice follow-up to this one, and that is at 12:15. I hope to see you there. Thank you for coming. Thank you very much for your contributions.